Welcome to the lab. Today, we will analyze the process of converting this exercise bike into a generator. The sturdy carbon steel bike frame serves as an excellent mechanical foundation to withstand loads at extremely high RPMs. Although the electronic display is broken, the drivetrain, belt, and mechanical flywheel remain intact. This project was inspired by grid power outages, which created a pressing need for an independent backup power source. The heart of the system is a three-phase, brushless DC motor, salvaged from industrial equipment, paired with an Sequel 50A three-phase bridge rectifier, which converts alternating current into direct current. A quick manual test shows that the DC voltage through the rectifier lights up a 12V LED strip, confirming the initial electromagnetic induction efficiency. To optimize the gear ratio, a large diameter, cast aluminum pulley was chosen to be mounted coaxially with the original flywheel. This flat belt will transmit all the torque with high grip and maximum slip resistance. Starting the teardown process, an impact wrench is used to break the locking nut connecting the crank arm to the bottom bracket. Combining wrenches and specialized tools to completely remove the mechanical pedal assembly from the main frame. Completely remove the two plastic side covers, exposing the extremely heavy magnetic flywheel assembly inside. Test fitting the aluminum pulley assembly onto the flywheel and using a marker to mark precisely the positions for the mounting holes. Moving to the drill press, using an HSS drill bit to punch through the marked spots on the flywheel's profile. The technician prepares stainless steel hex socket bolts with flat washers to firmly tighten the clamping assembly, using a cordless drill to lightly tighten the bolts, pressing the aluminum pulley assembly flush against the outer edge of the flywheel's chrome rim. The rear flange is locked with threaded nuts, creating a rigid mechanical connection against vibrations. Hand tightening the nuts temporarily holds the pulley block in place before applying maximum mechanical torque. The final torquing step, using a high torque impact wrench, ensures the pulley assembly is securely locked at high RPMs. Moving on to fabricating the mount. The distance from the flywheel assembly to the frame rail is calculated meticulously. Grinding off all powder coating on the steel frame, using an angle grinder, creating a perfect bare metal contact area for welding. A load-bearing square steel tube is measured and cut with extreme precision, using a high-speed abrasive chop saw. Using a MIG arc welder, the steel tube is welded directly to the longitudinal rail of the main bike frame, adding multiple layers of weld metal to enhance penetration, helping the joint withstand axial vibration impacts. The metal flywheel assembly with the integrated aluminum pulley is carefully reassembled onto the main axis of the support frame. Closely observing the mechanical clearance between the pulley and the frame, the extremely narrow gap proves excellent tolerance. Calculation skills. Stretching the drive belt over the large aluminum pulley groove completes half of the primary drive. Mechanism structure. The original rotor shaft of the motor has a diameter that is too small, completely incompatible with the secondary pulley. Placing the aluminum blank on the lathe to machine a concentric bushing, completely resolving the shaft diameter discrepancy. Drilling radial holes along the core of the aluminum blank, continuously spraying cooling oil to the finished metal surface achieves maximum smoothness. Mechanical vise to prepare a support base for the process of friction pressing. Precisely press-fitting the aluminum sleeve onto the rotor shaft, creating a friction joint with an interference fit that has extremely high mechanical rigidity. Directly screwing the grooved pulley assembly onto the newly sleeved aluminum shaft end, completing the shaft upgrade for the generator motor. Welding, tacking a small steel flange onto the horizontal rail assembly. From earlier, creating a support base with an absolutely flat contact surface. 4. The motor block is firmly positioned on the support base with 4 bolts tightened in a crisscross pattern to evenly distribute the force applied to the steel flange. 5. Trial fitting the motor base assembly onto the bike frame, while tensioning the belt, to align the coplanarity of both pulleys. Once the position is determined, and the locking bracket has standard belt tension, proceed to fully weld the motor base assembly to the main rail. The completed motion mechanism. The large aluminum flywheel drives the tiny pulley, creating a gear ratio that amplifies the rotation to a highly impressive degree. 1. Carefully assembling the protective plastic side covers to maintain the original aesthetic form, while shielding the rider from safety risks. 2. Undergoing the mechanical test, the pedaling cycle is very smooth, generating no strange noises. The transmission coordination system is extremely seamless. 1. A digital multimeter is connected in parallel, with 2 probes directly attached to the DC output of the rectifier circuit board. With just a leisurely pedaling pace, the DC voltage quickly surpasses the 18V threshold. The electromagnetic induction efficiency is excellent, maintaining a steady RPM. The voltage response is incredibly linear and stably fluctuates around the 24V to 26V mark. Once the rider sprints the DC electric speed, motor block is firmly, the peak voltage shoots up to approximately 30V, showing an extremely abundant output energy range. Power, 2. As the pedaling force is gradually reduced, the voltage immediately drops, providing an extremely vivid illustration of the principle of converting mechanical energy into electrical energy. 3-4. To supply current to household appliances, a circuit board inverter is connected to convert 24V DC into AC power. 4. Set the multimeter to the AC voltage measurement mode, measuring directly at the output of the inverter board. With just a slight nudge of the pedals, the inverter starts up, providing an extremely stable AC power supply, locked firmly at the standard 220V mark. The technician connects a panel with multiple E27 light sockets to establish a dummy load system with multiple power levels. The first practical load test uses an incandescent light bulb with a traditional Dian Quang design, reaching 25W in power. The 25W bulb lights up brilliantly instantly. Because the power consumption load is too small, the magnetic braking force on the rotor is almost negligible. Upgrading the test load to be more rigorous by screwing in series an additional high-power incandescent bulb of 40W into the chain. A total load of 65W makes both bulbs shine brightly. According to Lenz's law, the generated magnetic field starts to create resistance, making pedaling heavier. An extreme, super heavy load test, connecting a giant incandescent light bulb with a power output reaching the 200W threshold to the board. The 200W bulb only glows dimly. The excessive load surpasses the input torque amplitude, causing the pedal assembly to brake to a halt. Deciding to completely remove the incandescent lighting system, providing the clearest evidence of its inefficiency and terrible heat energy waste. 3. Slow, unloaded pedaling motions help the user relax their muscles and completely dissipate the magnetic energy. Field still trapped in the stator. 1. Exploring a new generation luminous flux lighting solution, an ultra-bright 50W plastic corn LED bulb, bringing optimal efficiency. 2 50W LED bulbs are screwed in parallel, re-establishing the power consumption load. The current stabilizes at the 100W power threshold. Amazingly, the 2 LED clusters instantly light up the space with blinding brightness, while the resistance torque on the pedals remains incredibly light. The technician decides to squeeze out the maximum power of the inverter by adding an auxiliary LED cluster to the electrical grid. The generator excellently handles the 3 LED loads. The alternating current remains absolutely stable, and the light does not flicker. For the final extreme full load test, 4 high-intensity LED bulbs are fully activated, ready to show off their illumination. The studio lighting system is shut off. The human-powered mechanical generator station immediately shines brightly, overpowering the entire room space. Today, we will test the actual load of this bicycle-powered generator system. First, the author removes some electrical load to check the system's response level. When the load decreases, the mechanical resistance also drops significantly, making pedaling much easier. The LED bulb shines brightly and steadily, proving the generated current is quite smooth. Continuing the test, the electrical connections are rewired to increase the power. The stepper motor acts as a generator, completely converting kinetic energy into electrical energy for lighting. Now it's a test with a user who has less physical strength, specifically a young boy. The boy starts pedaling, and the 4 bulbs instantly light up. The system starts up very responsively. To push the limits, a higher wattage bulb is introduced into the load circuit. When the load suddenly increases, the magnetic force locks the rotor tightly, making it almost impossible for the boy to pedal. The author proceeds to prepare a test with a bulb of up to hundreds of watts. The electromagnetic resistance is now too immense for a child's muscle strength. An adult steps in. The high-power light source flares up right at the first pedal stroke. The stable RPM helps the bulb maintain its blinding brightness. The conversion efficiency is extremely impressive. The third test involves an industrial light source. The spotlight mounting bracket is attached to the tripod. The wires are routed and connected directly to the output of the homemade generator. We check the magnetic friction level again, against the boy's physical strength. Once again, the spotlights blink continuously because the rotation speed is insufficient to provide a stable current. Upgrading the load with 2 AG LED spotlight modules. 50W outdoor specific IP 66 rated. The total load power is now 100 W, requiring quite a large torque from the mechanical shaft. As the author pedals, both spotlights instantly shine brightly, banishing the darkness in the room. The generated current is strong enough to maintain maximum power for both of these heavy load devices. Moving on to test smart devices. Here is a Samsung fast charger rated at 25 W. 3 chargers are plugged into the power strip one by one, receiving power directly from the generator. The cables are connected to 3 smartphones, including a foldable device. A close-up of the generator motor block, coaxially coupled with the exercise bike's flywheel, starting to generate kinetic energy. Please pay attention to the turned-off screens of the mobile devices. Perfect. All 3 devices receive charging current and display battery percentages, almost simultaneously. The belt drive spins the flywheel rapidly, providing continuous AC power to the outlet. The touchscreens still work normally, proving that the electrical pulses don't interfere with the phone's motherboards. Charging 3 phones at the same time doesn't seem to put too much pressure on the pedaler's legs. The pace is maintained steadily to simulate a real-world, long-term charging process. The output voltage is controlled extremely well through the author's steady pedaling speed. The most interesting part is the practical application. The whole family is gathered around for dinner. Suddenly, a simulated power outage occurs. The scene plunges into complete darkness. The human-powered backup system is activated. The father immediately pedals to power the floodlight. He pauses for a beat. The light goes out instantly, proving that there is no storage battery. The pedaling continues, bringing the 100 W powerful light back to the family dining area. To keep the dinner going, the wife has to feed the generator, which runs entirely on human power. A drop in pedaling speed means a voltage drop and an immediate loss of light. The light comes back on. This is truly a physical trade-off for energy, demonstrated very intuitively. Now it's the boys' turn to take over the shift, pedaling hard to maintain the light for the meal. Chewing food while pedaling against a 100 W load is a real endurance test for the boy. After a while, the father has to step back in, taking over as the main generator to stabilize the voltage, providing mechanical work, while simultaneously consuming biological energy, creates a rather humorous scene. Despite the hard work, the quality of light, produced perfectly, meets their living needs. A fantastic DIY project, and a perfect demonstration of the principles of physical energy conversion.